Welcome to section 2.5, implicit differentiation. And I have a note here that we're going to only do part of this section, so go ahead and skip related rates and examples 3 through 7 in the text. When we are given y equals 3x squared plus 5x minus 7, our function has been explicitly stated. We can then find y prime directly, the derivative. Y prime is equal to 6x plus 5. We can see it. It's explicit. New. Now there will be an assumption that y is still a function of x without it being explicitly stated. For example, x squared plus 5y squared equals 45. We could potentially solve this for y, but it's messy with positive and negative square roots. And here in 3x to the fourth plus 6y to the fourth minus 5y cubed equals 5x to the fourth minus 2x. I do not know how to solve this for y. So there's not really a way to make y explicit. Y equals some function of x. So we have to work with y being folded into our equation. When we take the derivative of an x term, the usual rules will apply. But when we take the derivative of a y term, the chain rule will kick in and we'll multiply by y prime. And again, if we knew what y was explicitly, we could just take the derivative and write it out, but that's the best we can do, is to tack on a y prime. So let's just give some examples. The derivative of x cubed will still be 3x squared, like we're used to. The derivative of y cubed will start off the same, 3y squared, but then the chain rule will kick in and we'll multiply by that extra y prime each time we actually take the derivative of a y. So in a typical problem, the x variables and the y variables will be mixed together. The two steps are, sorry for the scrolling, we take the derivative of both sides using the chain rule and product rule as needed, and then we'll solve for that y prime. In other words, isolate y prime on one side so we can say y prime equals. And I'll say the answer may contain both x and y variables, just like the original equation. So here's our first example. Find y prime and evaluate it at the given point. So here's our equation given x squared plus 5y squared equals 45, that example from up above, and our point 5, 2. So our thinking step, and you might want to write this out for now, eventually maybe not do this, is we're going to take the derivative of each term, derivative of x squared plus the derivative of 5y squared equals the derivative of the 45 on the right-hand side. So x terms operate as they always have. So the derivative of x squared would be 2x. The derivative of 5y squared behaves the same way to start. So we'll get a 10y. But then because of the chain rule, because y is an implicitly stated function of x, we get a y prime right there when we take the derivative. And then on the right-hand side, we get a 0. And for sure, if you prefer the dy dx notation for the y prime, that's totally fine. So I'll put a note here. Because it can get a little confusing with the y prime. Is that a y to the first power or is it a y prime? So totally fine if you prefer that notation. All right, so now I need to solve for y prime. So I'm going to go ahead and subtract the 2x over, because that does not have a y prime in it, that term. So the 10y y prime is equal to negative 2x. And then I'll divide both sides by the 10y. So my answer would be y prime equals negative 2x over 10y. And then I can reduce a little bit, that common factor of 2. So for a final answer, y prime would be equal to negative x over 5y. There is our derivative. It does have x and y in it. That's okay. So then we want to answer the second part of the question. We were given a point, so we want to evaluate it at the point 5, comma 2. So at the point 5, comma 2, y prime would be negative x, negative 5, over 5 times the y value of 2 would be negative 1/2. So that would be the answer to the second part of the question. So y prime itself, and then evaluate it. Now what I have to the right here is a graph of this equation. It happens to be an ellipse. We just found the tangent slope at the point 5, comma 2. And right here, I've got marked on the ellipse, that is our point 5, comma 2. And if we look at the tangent line at that point, hard to guarantee that the slope is negative 1/2, but I do see that the tangent line has a negative slope. And it certainly could be possible that that slope is negative 1/2. Pick a different point along the ellipse, and you get a different slope. So there's our first example. Let's do some more. Here's another one that's fairly straightforward. Here, I'll go ahead and scroll all the way to the top. Example number 4, find y prime for that other equation. That was my first early examples. 3x to the 4th plus 6y to the 4th minus 5y cubed equals 5x to the 4th minus 2x. This time we do have two terms with y's in them, so they both will give us y primes when we take the derivative. Here we go. Again, you might want to do the thinking step just to help your eyes kind of sort out what it is you're looking at. So derivative of each term individually, noticing when there's a y. It might not be worth writing this stuff out. Here we go. So each time I take a derivative of a y, I have to get a y prime attached to it. So derivative of 3x to the 4th would be 12x cubed, then plus 24y cubed, stick on a y prime there, and then minus 15y squared, stick on a y prime, because we took the derivative of y, and then on the right hand side equals 20x cubed minus 2. All right, so now to solve for y prime, we're going to go ahead and leave the two terms with y prime where they are. And in fact, I'm going to factor out that y prime from those two terms. And I'll go ahead and move the 12x cubed over. I'll subtract that over. So after I do that, both of those things, factoring out the y prime, I get y prime times 24y cubed minus 15y squared. And that equals 20x cubed minus 2 minus 12x cubed. Well, it looks like we've got some common factors. I didn't notice that, so I'll change that to 8x cubed minus 2. So then, our common terms, right, like terms, we could combine. So now I can just go ahead and divide by this bit that I factored out a y prime. I can divide by all this stuff in the parentheses. So for an answer, y prime will equal 8x cubed minus 2 over 24y cubed minus 15y squared. And then common factor is always a possibility. These things rarely reduce, but sometimes they do. So you might want to go ahead and factor to see if this reduces at all. So on the top, there's a common 2. So 2 times 4x cubed minus 1. On the bottom, let's see, it looks like a 3 that's common and a y squared. So 3y squared, left over would be 8y minus 5. Oh, and I don't see anything reducing. I tried, but it didn't reduce. Never hurts to factor out, so I'm just going to leave it factored and give that as my final answer. I don't mind too much if you give the original unfactored version, as long as you check, at least check to see if it reduces. And there we go. So there's our first two examples. Gets a little bit more complicated after this, so I'm going to come back for a part 2.